Okay, so we are now going to start a new section. Having seen quite a few things in field theory, in this section we are going to see how those things, those results that we have already seen can be applied to answer some problems in plain Euclidean geometry. So this is the section, its name is Construction with Straightedge and Compass. And this is something we have already come across quite early in our mathematical training, namely in school. You remember we were asked to construct some figures with only straightedge and compass, and this kind of constructions require that we do not measure any length of a line segment and then draw it. Without measuring lengths, we are to draw figures in the plane of your paper using only straightedge and a compass, using which you can of course draw curves and circles. So let's see how the section starts. So it starts like this. The author says, we pause in our development to examine some implications of the results obtained so far in some familiar geometric situations. Okay, and now the author defines something like this. A real number alpha is said to be a constructible number if, well, let me write the actual sentence. If by the use of straightedge and compass alone we can draw a line segment of length alpha Okay, just looking at this statement, it seems like it's an okay statement. A real number alpha is said to be constructible if you can draw a line segment of length alpha using only straightedge and compass, like how you used to draw such figures in school. But unfortunately, this statement is not true for one simple reason. If your alpha is, say, -1, then the statement doesn't make sense for that value of alpha, or in fact for any negative real number alpha, since nothing here tells us that alpha has to be a positive real number. The statement does not make sense when alpha is negative. That is because a line segment of length alpha is being mentioned, and length cannot be negative. But then you may say that, okay, then negative numbers, maybe they are not constructible numbers. That's why we only have to consider positive real numbers and then see if any one such number is constructible, any such given positive real number is constructible or not. The definition does not apply to negative real numbers. You may think like that because we are saying length alpha. Unfortunately, that is not true. We will see why soon. Then the author continues, we assume, and because we are talking about length, we assume that some unit length is given. We are given some fundamental unit length. Okay, and then he continues, recall from high school geometry that we can draw with only straight edge and compass, a line parallel to and a line perpendicular to a given line and passing through a given point. To a given line and passing through a given point, and using this one can prove that if alpha, beta are constructible numbers, then so are alpha plus or minus beta, alpha beta, and when beta is not equal to 0, alpha over beta. Okay, so that is the definition of constructible number Herstein is using, which I am saying is a little wrong, especially when the alpha is negative. Then the definition just simply doesn't make sense, which may make you conclude that the definition is not applicable to negative real numbers, making negative real numbers not constructible. One may not see that there is something wrong with the definition at once, but once one thinks of negative real numbers, then one concludes that the definition is not applicable to them. So by definition, negative real numbers are not constructible. But I have also added that that is not the case. But why? Anyway, let's see after that. So what else is the author saying? And of course, because we are talking about length, some fundamental unit length in the plane is given, which may be this much or this much. It actually does not matter. It depends on us. Now, we are then led to recall one fact from high school geometry, that if we are given a point and a line in the plane, the point may lie on the line itself, okay. Then using only straightedge and compass, we can construct a line parallel to this line, given line, and passing through that point, and also another line perpendicular to the given line and passing through that point. It's a fact that is there, that fact is true, okay. And using this fact, one can prove that if alpha and beta are two constructible numbers, then so are their sum, difference, product, and quotient, provided the quotient can be formed. Okay, so from this, what is your natural conclusion? The natural conclusion is that the set of all constructible numbers, which clearly is going to be a subset of the set of real numbers, is actually a subfield of the field of real numbers. That's what we conclude from this fact. So that is the next statement. And one more thing. In fact, exactly what Herstein says is this: using this, it is an easy exercise to prove that these things are true. And regarding that, he writes, see exercise 1. And then the final conclusion here in this paragraph is this. So the set W of all constructible numbers forms a subfield of the field of real numbers. Forms a subfield of the field of real numbers. So if we believe that this final statement here up to this point is true, then the W, the set of constructible numbers, is a subfield, and being a subfield of R, the field of real numbers, W includes all the rational numbers in it, and as such, automatically negative rational numbers also must be in W. That means at least the negative rational numbers should be constructible if we believe that this statement is true. But according to them, that means, for example, -1 should be constructible. But then you apply the definition of constructible numbers that we have in this text to -1. According to that definition, we should be able to get 2 points. Or rather, we should be able to construct a line segment using only straightedge and compass, whose length is -1. And that is simply nonsense. It does not make any sense. Length is not minus. Length can be 0, length can be positive, but length is never negative. So there is a slight mistake. And now we have to rectify that mistake, and also we have to make clear or make precise what do we mean by construction with straight edge and compass. So that we will do now by actually solving exercise 1 now itself, so that in the beginning itself things are set straight and we can then see what else the author has to say after we show that yes, W is a subfield of the field of real numbers. Okay, so let us start. So the exercise 1 is just this. Prove that if alpha comma beta are constructible, then so are, that means basically just this. So are alpha plus or minus beta, alpha beta, and alpha over beta when beta is non-zero. The solution. In the solution, we first of all define what we mean by construction with straightedge and compass by defining some operations that we are going to call straightedge and compass operations, some geometric operations. And in the beginning, I think we are going to, so that will come afterwards. Okay, so let me write like this. The following are defined to be the compass and straightedge operations, or straightedge and compass operations. So you can switch the order also, it will mean the same thing. There are 3 operations, and I have not made these things up. Actually they are there, you can see in that part of Euclidean geometry where you have these constructions. The first one is this. Draw a straight line through 2 given distinct points. If 2 distinct points in the plane are given, then, and we are of course talking about things in the Euclidean plane, okay, not in 3D space but in the Euclidean plane. If 2 distinct points are given, then we can draw a line through them. That is one operation. Okay, so if 2 such points are given, then we get a line. B. Set a compass radius equal to the distance between two given, of course, distinct points and draw a circle with this radius, that is this length as radius, this distance as its radius, and any point as center. And any point as center. And part C, there is another operation. Draw points at the intersection of two given lines or two given circles or a line and a circle. So let us again go through the operations once more. If 2 points are given, then you can draw a line through them. That is our operation A. Again, if 2 points are given, 2 distinct points, then you can take your compass radius equal to the distance between them and then draw a circle anywhere, that is with any point as its center and with its radius equal to that length. That is the second operation. And the third operation is this: if you are given 2 points and they are intersecting each other, then you can draw a point at their point of intersection. Or if 2 circles are intersecting either like this or maybe they are touching each other just, then you can draw points at their intersection, giving you 2 points. Or if it is like this, then you draw that 1 point, so you get points. Or if a circle and a line are intersecting, maybe like this, say the line is a tangent, it's a little above the circle, but you get the point. Then you draw a point here, you get 1 point. Or if the line is intersecting the circle like this, then you get 2 points and you draw those points. So this is the third compass and straightedge operation. Now we are going to define constructible objects, not just constructible numbers, because we are going to need them. So this is our next definition. let two points P and Q be given in the plane R2 I just simply write to mention that to express the fact that we are in the Euclidean plane. Let's see. So 2 points P and Q are given in the Euclidean plane that are at a distance one apart. Okay, so say these two things are given. There may be any points which are at a unit distance apart from each other. A point line circle is what have I written? A point or a line or a circle in R2 in that same plane is said to be constructible if it can be drawn in a finite number of compass and straightedge operations starting from P and Q. Okay, so that means if you start from P and Q, those two fixed given points, and then apply the compass and straightedge operations, any number of them, finitely many of them, in any sequence you want, that is, say you apply the operation A first, you draw a line through those 2 points P and Q, you get a line. That line will be a constructible line. Or you may choose to draw a circle somewhere in the plane with its radius equal to the distance between P and Q, which is 1. So that circle will be a constructible circle. And then once you have those objects, then you can then draw further objects, further points, lines and circles, and they will be constructible. And if you are thinking, how will they be constructible? For example, I have not completed this now. Compass and straightedge operations starting from P and Q. So before we continue the solution, let us actually construct some objects. So this is my P and Q, or why have I drawn it there? I can draw it in the middle. No? So I can apply operation A and draw the line that passes through them. So that means to get to this line, I have applied the compass and straightedge operation A, and that tells me that this line is constructible. So it's a constructible line. And then you can then, okay, what else can you do after this? You can take this distance between P and Q as your compass radius, and you can draw a circle anywhere in the plane. Say you draw a circle with P itself as its center, then the circle will pass through the point Q and will go like this, and it will of course intersect this line at another point here somewhere, which will also be at a distance 1 from P. So note that you now have a given line, and after drawing this circle you have a given circle. And one more thing, the circle by definition will be constructible. And now you have a given line and a given circle. One of the points of intersection of this line and the circle is Q, which already is one of the existing points. But you get another point, which is a point of intersection of the circle, the given line and the given circle. So by operation C, you can in fact first of all draw a point there. And now by the definition of constructible objects, that point will be constructible. And this way you can do many things, and you can create more and more constructible figures. And it's a fact that if you go like this, you can, by some methods, not obvious, but they are there, you can draw a line parallel to a given line, that means parallel to a constructible line and passing through a constructible point, by using only straightedge and compass operations, and also another line perpendicular to the given line and passing through that given point. So these two lines will be constructible, and then intersections between these lines and other lines or other circles will give you more constructible points, and so like this it will just simply blow up. Okay, so now you get the idea of how to use those compass and straightedge operations and what sort of figures you can get. You can in fact get many different types of figures. Just this simple example does not show the full variety of figures that you can get, but you get the basic idea. Okay, so now we continue our definition. The definition is not over yet. So we have said that a point or a line or a circle in R2 is said to be constructible if one can draw it in a finite number of compass and straightedge operations starting from P and Q. But then we continue our definition. So I can continue from here itself. An angle theta degree. This also is something we will need, where theta lies between 0 and 180, like this, is said to be constructible if it's an angle between two constructible lines. I say an angle because once two lines intersect, there are two measurements of angles, right? Two opposite angles which are of equal magnitude and two other opposite angles. So it is any one of them. If it happens to be an angle, such an angle between two constructible lines, then we will call it a constructible angle. And now finally we come to that thing that a real number is constructible. So that small mistake that the author made, we are going to rectify it naturally like this. A real number alpha is said to be constructible if there exist two constructible points in the plane, of course, that are at a distance this apart from each other. This now makes sense because this is a non-negative real number, so it can be a distance. And now our definition is finally over. And now we start the actual solution. So the first thing we are going to prove is that the sum of alpha and beta is constructible. We now prove that alpha plus beta is constructible. So we deal with the trivial cases first so that we can get rid of them in the beginning itself. It is trivial if alpha is 0 or beta is 0, because if at least one of them is 0, say if alpha is 0, then this sum is just beta, which is already given to be constructible. So we assume both alpha comma beta are non-zero real numbers, and keep in mind that it is given that both of them are constructible. Now, by this definition of constructibility, what does it mean for alpha to be constructible? It means that in the plane there are two constructible points somewhere such that the distance between them is this. That's what it means for alpha to be constructible. But there are some other things that we need to do before we go to that part. We assume without loss of generality that this absolute value is greater than or equal to that absolute value. I mean, in general, it will be the case that one of them will be greater than or equal to the other. Equality is also a possibility, so we have allowed for that possibility, or they may be they may be different. One may be strictly greater than the other. So this captures all the possible cases. Okay, now let small p and small q be 2 points, 2 constructible points at a distance absolute value of alpha apart. We draw the line passing through P and Q. This line is constructible. So now we are going to do a little drawing. So because alpha is given to be constructible, P and Q exist somewhere in the plane. So what we have done is this. This is our P. This is our Q. Keep in mind that these are not capital P and capital Q. They are points that are given in the plane, fixed points which are at a unit distance apart from each other. However, these are some points P and Q, and the distance between them is this. Okay, and we have drawn the straight line passing through them. So by the definition of constructible lines, this line is constructible. Now what? Let me extend this a little more on that side. Now, draw a circle with center at Q and radius this. That circle will look something like this. Okay, but the question is, how are we allowed to do this? Yes, we are allowed to do this, but why? Because it is given that just like alpha, beta is also constructible, so by the definition of constructibility, there exist two constructible points somewhere in the plane where we don't know, and it does not matter, such that the distance between these 2 points is this. And by compass and straightedge operation B, the second one, we can take the compass radius equal to this distance between these 2 constructible numbers, and we can draw a circle anywhere on the plane with that radius. We have chosen to draw that circle with Q as the center. So that means this circle is a constructible circle. This circle is constructible. Let this circle intersect the line through P and Q at U and T. So this point is U, this point is T, where we need to of course mention which one sits where U lies on the line segment joining P and Q, and T is the other one. Okay, now let's see what the distances here are, so that we can see everything clearly. This distance is alpha. Alpha means this alpha, of course, absolute value of alpha. This distance is, we can get rid of this. This distance is beta. And of course this distance is also beta, or absolute value of beta to be more precise. Okay, so alpha, the distance, absolute value of alpha, the distance between P and Q, and due to this circle being of radius this much is this distance, this much is also this distance. Okay, but the question is, what is the guarantee that U lies between P and Q? That is because in the beginning itself we have assumed that the absolute value of alpha is greater than or equal to the absolute value of beta. So this much is greater than or equal to this much. That's why U lies between P and Q. But in case you have equality, actually P and U coincide. That possibility is also there. So we just simply mention this. Note that P and U if this is equal to this. Okay, so this is our setup. Now we are going to use this setup to prove that alpha plus beta is also constructible. That means we have to show that there exist two constructible points in the plane such that the distance between them is this. If we manage to show this, then that will prove that alpha plus beta is constructible. And now, because we are going to deal with alpha plus beta, cases will arise. Actually, many cases arise if we do not assume anything like this, but this makes the number of cases relatively small. We will now see why. Let us first deal with the simplest cases. If alpha is greater than 0 and beta is greater than 0 as well, keep in mind in the beginning itself we have already dealt with the case where either alpha or beta is 0, or maybe both are 0. So now our alpha and beta are both non-zero. So if they are like this, then there is no possibility of any one of them being 0. If they are positive, both of them are actually positive. Then clearly alpha plus beta is also positive, and hence the absolute value of alpha plus beta is just simply alpha plus beta. But due to these inequalities, this is also equal to this plus this. So that means in this case we want two constructible points here somewhere so that the distance between them is this plus this. And from the figure you can clearly see that two such constructible points are P and T. Have I mentioned that U and T are constructible? No. So I need to mention that here after you complete this sentence. Here you continue. Note that U and T are constructible. Okay, and then after that you start like this. The constructible points P and T are at a distance this. So that means at least in this case we have actually found two constructible points such that the distance between them is this and hence this. But that is not the only case, there are others also. If both alpha and beta are negative, then alpha plus beta is also negative, and hence so the absolute value of alpha plus beta in this case is going to be minus of alpha plus beta, because alpha plus beta is negative, which is minus alpha minus beta. But because both alpha and beta are negative, minus alpha is the absolute value of alpha and minus beta is the absolute value of beta. So again, in this case also, the constructible points P and T are at a distance this. So this case also has been settled. Now if alpha is greater than 0 but beta is less than 0, then what was it? I forgot the trick that we have here. Then we need to first of all figure out what alpha plus beta will be, more specifically what its sign can be. So alpha plus beta in this case, because alpha is positive, alpha is absolute value of alpha, and because beta is negative, beta is not the absolute value of beta, but minus beta is the absolute value of beta, or in other words, beta is this. But due to our inequality, this is greater than or equal to 0. So in this case also alpha plus beta is non-negative, and so its own absolute value is just simply alpha plus beta. But now alpha plus beta is not this, but rather this difference. Now we need two constructible points such that the distance between them is this, and two such points are P and U, because absolute value of alpha minus absolute value of beta gives us this distance. The constructible points P and U are at a distance this. Okay, now finally we consider the only remaining case where alpha is negative but beta is positive. Note one thing clearly, that if you have already encountered such arguments where you have two real numbers and you have to consider these specific 4 cases depending on the signs of the real numbers, then in some such problems you may not have had to consider this last case where alpha is negative and beta is positive. And that is the case if the problem at hand that you are dealing with is symmetric with respect to alpha and beta. That is, the problem does not change if you interchange alpha and beta. In this case, that's not what we have because of this inequality. The status of alpha and beta are not the same. So you have to also deal with this last case. If alpha is negative and beta is positive, then alpha plus beta, this time it's going to be the exact opposite. And due to this inequality, this one is no longer non-negative but it is non-positive. And so this is minus of alpha plus beta, which will be minus of this, that means this. Okay. So again we need two such constructible points such that their distance is this. Again P and U. Again the constructible points P and U are at this distance away from each other. So now we have completed our giving for all the cases, and in all the cases we have in fact found constructible points which are at the desired distance away from each other. Thus alpha plus beta is constructible. Note that this implies alpha minus beta is also constructible. Why? We have proved that for any alpha and beta, alpha plus beta is constructible. So that automatically means that alpha minus beta is also constructible. But how exactly? This is because minus beta is constructible. And why is that so? What does it mean for beta to be constructible? To have two constructible points such that the distance between them is this real number. But then the same two constructible points are also at this distance, which they are the same real number. So it proves that from the constructibility of beta, it follows that minus beta is also automatically constructible. So that's why alpha minus beta is constructible, because just now we have proved that the sum of two constructible numbers is constructible. Okay, so that settles the case for sum. Now we show that alpha beta is constructible. And here also there are some trivial cases, so let's deal with them first. It is, now we will not need this figure, but we will need another one. It is trivial if alpha belongs to 0, 1 or beta belongs to this. So we assume that none of them belongs to this set. Okay, by the way, how is it trivially true that alpha beta is constructible when either this is the case or that is the case? So what goes on when alpha is 1? That is easy to understand. When alpha is 1, this product is just beta, and beta is given to be constructible. But what happens when alpha is 0? Then this product is 0. Is 0 constructible? Yes, it is. Why? That is because, you see, like it's precisely like this. Remember, we are already given in the very beginning itself that 2 points are there which are at a distance 1 apart from each other, and they are by definition constructible. So the number 1, the real number 1 is constructible. So by what we have proved just now, 0, which is 1 minus 1, also has to be constructible. So that's how 0 is constructible. So you do not need to consider that case. I mean, we have considered, and in that case it's trivially true. So now our alpha and beta are both neither 0 nor 1. We also assume that both alpha and beta are positive. Okay, why do we not have to consider negatives at all? That is because if, say, your alpha is positive but beta is negative, then you have the product alpha beta which is negative, right? But say you only have proved this case. Say you have proved that alpha beta is constructible only when alpha and beta are positive. But then constructibility of beta, which is given, already implies that minus beta is constructible. So minus beta is positive. So according to this result, alpha times minus beta will be constructible. But that means what? That means there exist two constructible points such that the distance between them is this product, which is this not this product but this thing, but that is also equal to this, which means that two constructible points are there such that the distance between them is the absolute value of alpha beta. That automatically tells us that alpha beta is constructible. So we do not need to actually worry about the other cases depending on how the signs are of alpha and beta. So that's why we just simply assume that both alpha and beta are positive. But still two cases will arise depending on whether alpha is greater than 1 or less than 1. Keep in mind, we already are not considering alpha to be equal to 1. Okay, now we will need to start with these two given points P and Q, which are at a distance 1 apart. So let me draw the figure there. So this is how things will go here. We have the points P and Q. So this is P, this is Q. Draw the straight line L through P and Q. So this is our straight line L, and you of course understand that this L does not start here, but we have just simply not drawn that part. We don't need that part. We have drawn only this part, that side of P where Q lies. Then by the definition of constructibility of lines, L is constructible. Let R be the point on L such that the length of the line segment PR, so this is R, is alpha. R is constructible. Okay, but the question is, how are we choosing R? Are we allowed to choose this point R? Well, let's see. It is given that alpha is constructible. Okay, so that means there exist some 2 points in the plane such that the distance between them is alpha, and in this case it is actually alpha because alpha is a positive real number. In fact, alpha is greater than 1. So what you can do is that you can take your compass radius equal to this distance and draw a circle with that radius and with its center at P. That circle will intersect the line L at 2 points. One of those 2 points lies on this side, and that point is R, so that the distance between P and R will be alpha. Okay, so alpha R is a constructible point. That means we are allowed to consider this point R, and it will be constructible. We are going to assume that we can draw a line through a given point and parallel to a given line. By compass and straightedge operations. You will find this exactly how you will find this fact in the geometry literature. In fact, you go back to your construction that you have learned in school. There itself you will find this, and also that other one which has the perpendicular line. Okay, so we are going to not go through that once more. We assume that we know that. Okay. Now draw a line through P that okay, let me not write it like this. Draw a line L prime that intersects L at only P, something like this. I messed up this part. Okay, so this is L prime. This L prime can be like this or like this also, but keep in mind it has to pass only through P. It intersects L only at P using straightedge and compass constructions only, operations only. The question is how, and this part I leave to you to figure out. We, however, continue our thing, and we are going to okay, here I have called this okay, I can call actually here what I have written here, we have S here, but I am calling it R. It does not matter much. And this one, there we are going to have another point here. That thing I think I have called R or T. We will see. Just I should not make any mistake. Okay. Then L prime, because it can be drawn, that means L prime is constructible. Let T be the point on L prime such that the length of the line segment PT is beta. Let okay, then T will be constructible so T is a point here somewhere, so that the length PT, length of the line segment PT is beta, and this T also can be drawn just like how we have drawn R, because just like it's given that alpha is constructible, beta is also constructible. Note one thing, that although we have assumed alpha to be greater than 1, we have not imposed any such restriction on beta. The only restriction on beta is that beta is neither 0 nor 1. It may be greater than 1, it may be less than 1 also, and it does not matter. Okay, so T is constructible. So whatever points we have drawn here, they are all so far constructible, and these two lines are also constructible. The only thing that is somewhat not clear is how to draw this L prime. That I have left to you. Okay. Now the line, so before I erase this part, let me write the distances at least. This much is 1 and this much is alpha. And why does R lie on the right side of Q? That is because alpha has been chosen to be greater than 1 and this much is beta. Now the line L double prime passing through Q and T is constructible. That is this line. And we are not, of course, going to draw the full line because we need only this much. This is constructible. Actually, we are talking about the full line, but we need only this much. Why? Because it passes through two constructible points Q and T. That's why. Oh, the way we have, okay. The way I have drawn this and the way I have drawn R, I won't be able to show something with that we are going to need. So let me draw R a bit closer to Q. Okay. So the line passing through R and parallel to L double prime is constructible. So that means we are using that fact here, that through a given point and a given line and parallel to a given line, we can draw another line. Let this latter line intersect L prime at U. Then U is constructible. Because we have shown an acute angle between L and L prime, you may no, I don't think that is going to make any difference. So this is okay. Now, from geometry, the fact that this angle is acute has nothing to do with what we are doing. This angle may be a right angle also. So then these lines will be like this. Now from geometry, triangle PTQ is similar to triangle PUR. So, and after this, so I have to carefully write what I have here, because otherwise I may be going in circles. PU divided by PS is equal to PT divided by, okay. So, PU divided by PR is equal to PT divided by PQ. In similar triangles, corresponding sides are in the same ratio, that fact. This gives us PU equal to, note that PQ is 1, PR times PT. PR is alpha and PT is beta. So the distance between this constructible point and this constructible point U is alpha beta. Thus alpha beta is constructible. And note that here we do not need to consider that absolute value because both alpha and beta are positive. One can similarly handle the case where alpha is actually less than 1, and I want you to actually do this similarly like this. And in fact, okay. Should I conclude here once more that hence alpha beta is constructible no matter what alpha and beta are? I don't think that is needed, that is understood. In fact, similarly we can also show that alpha divided by beta is constructible when beta is not equal to 0. This similarly these parts are left to you. The only hint that I will give you is that you just have to take the lengths cleverly, so that after going through such an argument involving similar triangles, you end up having something like this, alpha divided by beta, or in this case also you end up having alpha beta. You play with these things, these figures, you will figure out. It's not that difficult. It's just a matter of getting the correct lengths and the correct triangles, that's it. And the figures are going to be exactly similar, nothing else, just something like this. So this completes the solution to exercise 1. I have decided to start the section with this solution itself, so that in the beginning itself we get many things sorted out. That's because the section starts off with a little vagueness. We may not be able to recall what construction actually entails, and also we needed to rectify that small, but I should not say small, it's a significant mistake, that of length alpha. Length alpha does not make any sense if alpha is negative. But now we have gone through all these things, and now we can say that yes, Herstein's statement is true. The constructible numbers form a subfield of the field of real numbers, and as such, the real numbers form an extension of the field of constructible numbers. And this idea is the link between geometry and field theory. And we will see in the next field theory video how this can then further lead us to some results which will enable us to answer some questions which the ancients struggled with. And without using field theory, some geometric problems cannot be answered regarding constructions. So we will see that in the next field theory video. And tomorrow let's do vector spaces. So that's just it for tonight. So see you tomorrow with vector space theory, again from Herstein's Topics in Algebra. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.